Okay, Assalamu alaikum. So in last class, we were discussing this question, which was in the sessional exam last year, I think, in which we had a truss, basically just two elements, in which there was a force applied somewhere. It wasn't shown on the figure, so I've just drawn it randomly at point 2 in the horizontal direction, in the x direction with 1,000 Newton force. Or we had to do a couple of things. We had to find the deflection at some point P. We had to find the stress in this at this point P, which means in this element 1, and then we had to find the natural frequency of this truss. Okay, so this diagram comes from example 12.5 of the SS Rao textbook on FEM, which I realized very late, honestly. But example can there is no applied force and there's no point P, so I sort of there's a modification of that example, and the values of density and E are also somewhat different. Okay, but do have a look at this example if there's something that's unclear in this explanation. Okay, so originally I was actually just writing this out while recording this video, but it turned out that if you run out of computer space while you're recording, then the recording sort of goes to waste. It doesn't really save. So अब सब कुछ solved है आपके सामने, so it's not ideal. I wanted to do this in front of you guys, but still, at least I'll be able to get through this video in like 5 minutes. So I guess there's this. It's not all wasted, right? Okay, so हमें इसमें क्या चीजें चाहिए होंगी? We need ये ट्रसेस के लिए ट्रांसफॉर्मेशन इक्वेशन फॉर एग्जांपल हमें चाहिए पड़ सकती है, ट्रांसफॉर्मेशन मैट्रिक्स की जरूरत पड़ सकती है, स्टिफनेस मैट्रिक्स और मास मैट्रिक्स की जरूरत पड़ सकती है. ठीक है, सो वन सेट ऑफ इक्वेशंस दैट विल बी अवेलेबल टू यू, not just a set of equations, basically honestly notes ही हैं, very brief 2 pages worth of notes. In any assessment अगर physically हमने की सेशनल टाइप की, तो उसमें ये 2 पेजेस के एक ब्रीफ नोट्स जो कि मैंने अपलोड किए थे वो अवेलेबल होंगे. ठीक है, सो इसमें द थिंग्स टू लुक एट आर फॉर दिस प्रॉब्लम इज ये मास मैट्रिक्स फॉर ए 2D truss element and the stiffness matrix for a 2D truss, and also transformation from a local coordinate system to a global coordinate system can be useful. You don't necessarily have to use this, but still it can be useful. हमने सवाल में इस्तेमाल किया हुआ है. ठीक है, okay, so many ways to approach this. एक approach ये है कि आप इसको element 1 कह दें, इसको element 2 कह दें. ये आपके nodes हैं node 1, node 2, node 3, let's say. Node 1 पे displacement in the x can be called u1. This can y can be called v1. This could be called u2. Y it could be called v2. And x direction में displacement of 3 is going to be called u2, and y direction displacement of 3 is going to be called v3. U3 and V3. Okay, so SS की जो textbook है उसमें that's not the designations that they use, but you're gonna have to come up with your own coordinate system and designations in any question that you might solve, and you should like mention that rather clearly. Honestly, मैंने भी नहीं लिखा हुआ. I should like write all of these things down. ठीक है, कि मतलब for example this would be U3 and this would be V3. इस तरह तमाम जो 6 कोऑर्डिनेट सिस्टम्स हैं वो आपने लिखने चाहिए, और ग्लोबल कोऑर्डिनेट सिस्टम भी हमें लिखना चाहिए. I mentioned in class के one possible alternative way to do this would be कि notice कि ये angle is actually 90 degrees. So you could maybe just rewrite this, मतलब redraw this as two trusses at an angle of 90 degrees and a force applied accordingly in this direction, right, at this point. So इससे थोड़ा बहुत शायद simplify हो जाए. Not really, honestly, because ये भी 45 degrees है, so इस वजह से कोई खास ज़्यादा फर्क नहीं पड़ता है. This is simple enough, but इससे I guess even more simplify हो जाता, because आपके जो angles हैं वो 0 या 90 इस तरह के values होती, ना कि 45 or so on. So the way it's currently set up, ये जो आपके 1 से 2 one node or node 1 और node 2 के बीच में element है, that is at an angle of theta is equal to 45, and 2 और 3 वाला जो element है, that is at an angle measured from x in a counterclockwise direction comes out to be 360 minus 45, so 315 degrees, right? So stiffness matrix for element 1 is going to use L is equal to M, which is cos of theta, or sine of theta is equal to, but the sine of theta and cos of theta are both the same na, when theta is 45, which is just 1 over under root 2. So regardless of whether you have L square or LM or M square, the value is just going to be 1 by 2, right? जब यहाँ पे negative sign होगा तो बाहर भी negative, तो negative sign is going to remain there, but the values of all of these elements are really going to be 1 by 2. So 1 by 2 को हम बाहर लेके आ सकते हैं, यहाँ पे लेके बाहर लेके आ सकते हैं, and what you're going to be left with is just 1 or -1 depending on which element you are. So all of those elements के जहाँ पे कोई वो नहीं है, negative signs नहीं है, all of these are going to be plus ones, and all of these little elements के जहाँ पे the minus signs लगे हुए, all of these are going to be -1, and these correspond to the nodal displacements u1 v1 u2 v2, right? So ये 1 के लिए हो गया, element 1 के लिए हो गया. Element 2 के लिए theta is 45, so cos 45 is plus positive 1 over under root 2, sine minus 45, yeah, sine of 315 is minus 1 over under root 2. So what's going to happen is कि looking at this, जहाँ पे L square या M square या L square ये चारों तो सीधे सीधे जो है ना 1 रहेंगे, because प्लस हो या माइनस हो स्क्वायर कर देंगे तो इट्स गोना बी पॉजिटिव, राइट? जहाँ पे आपस में मल्टीप्लाई हो रहे हैं, सो वहाँ पे एक प्लस 1 over under root 2 minus 1 over under root 2 से मल्टीप्लाई हो रहा है, सो फिर you're gonna have a negative sign. So wherever you have ML, you're gonna, LM, you're gonna have a negative sign, and wherever you have minus LM, you're gonna have a positive sign, very obviously, right? So इस तरह ये पूरा हम बना सकते हैं. 1 over under root 2 में हम बाहर लेके आ गए, and the rest you can just write एक एक करके, ठीक है? And these corresponds to the nodal displacements u2 v2 u3 v3. Okay, so next up we have to assemble the entire thing, which is not entirely all that necessary, considering that our boundary conditions suggest that u1 v1 and u3 v3 are all going to be 0. So the only things that we need to look at are as just v2 and u2, and everything else, really there's no real need to even um, compile it. But इसमें the way to compile it is obviously these first, ये 4x4 वाला जो हिस्सा है, इसमें अगर ये प्लस के आगे प्लस 1 -1 प्लस 1 को इग्नोर कर दें, इसके अलावा जो लिखा हुआ है, that is, all of that is just equal to this k1 thing, and ये यहाँ पे इस इलाके में k2 ऐड हो रहा है, सिवाय इस 1 के और इस 1 के जो कि k1 से आया है, ठीक है? So just add things at their appropriate positions. Given K global stiffness matrix where you're going to find U1 V1 U2 V2 U3 V3, right? So यहाँ इन elements को उठा के यहाँ पे आप add कर सकते हैं. What makes this thing really easy is that the value of A, E, and L are the same in both elements. So all of that can be taken common. राइट? अगर ये ना होता तो दिस वुड हैव बीन अ बिट ऑफ अ मेस, अंदर बहुत सारे अजीब अजीब किस्म के एलिमेंट्स आ रहे होते, अजीब अजीब किस्म के नंबर्स आ रहे होते, ठीक है? ये force vector is going to have reactions at node 1 and node 3. So ये R1, R2, R3, R4 are reactions at node 1 and node 3, which you don't really have to find. All of these rows and columns are going to get deleted. उसके बाद force of 1000 newtons is added just at point 2 in the x direction. So this corresponds to displacement of ये u2 वाला जो point है ना, उसके across ये 1000 की value हमने लिखनी है. So जहाँ पे u2 आता है जो कि third row में, यहाँ पे 1000 की value लिखनी है, and there is no force in the y direction on node 2. ठीक है? So this is our force vector. All right, so if you get rid of all of these rows first, ये first, second, fifth, sixth, if you get rid of all of them, then you're going to be left with just um, ये 2 by 2 की equation जो कि f is equal to kx type की equation होगी, which is going to read a over l. ये this 2 is going to, by the way, cancel out the 2 जो कि अंदर आ रहा है, right? So the place to look at is this place right here, ये बीच वाला 2 by 2 वाला हिस्सा, which corresponds to, hello, which corresponds to um, ये U2 and V2, ठीक है? Okay, and similarly यहाँ पे you get 1000 and 0. So all we have to do is solve for U1, U2 and V2. Kind of obviously V2 is going to be equal to 0 and U2 is just going to be equal to 1000 divided by A over L. Okay? So 1000 multiplied by L, which is L1, which is the length of the element. If you think about the length of the element, I should, my तस्वीर बिल्कुल गायब हो गई है. This is interesting. Any idea? Okay, there you go. If you look at the length, if you try to find the length, it's kind of obviously 50 square plus 50 square under root, right? So 50 into under root 2 in centimeters. So meters made, it's going to be 0.5 under root 2, right? So the length of each of these elements is 0.5 under root 2. उसके बाद bottom पे you've got area which is 2 centimeter square. So centimeter square को meter square में convert करना है, तो you're going to get this into 10 raised power minus 4. And finally, the modulus of elasticity E is 210 gigapascal, so 210 into 10 raised power 9. Okay? This is the value that comes out, and V2 is equal to 0. Okay? So by the way, the displacement at point P is just going to be half of this U2, right? In the U direction. In the V direction, it's also going to be 0. मतलब in the Y direction. Okay, in the x direction, it's going to be half of this value. So P per this deflection was just as simple as that. I haven't really calculated it. You can do it, I'm sure. Okay, so उसके बाद अगर हमें stresses निकालना है, तो first we need to find strain. So strain निकालने के दो तरीके हैं. एक तरीका जो कि जरा intuitively बंदा निकाल सकता है is draw the undefined link 1. So undeformed, sorry. So in the undeformed element, your node 1 is at 0.00 and your node 2 is at 0.50 in centimeters, right? And in the deformed, when it gets deformed, after it gets deformed, origin is still at 0, sure, why not? Magar ab this point has moved a bit to the right? So originally ये जिधर था उसे थोड़ा सा राइट की साइड पे मूव कर गया, right? So now in the x direction it's 50 centimeter, या more accurately 0.5 meter plus u2 if u2 is in meters. So x में जो है ना it has deflected a bit towards the left. Y में nothing has changed, right? So by definition, the strain is the change in length divided by the original length. So the change in length is going to be length of the deformed element minus the original length divided by the original length. So the length of the deformed element is going to be 0.5 plus u2 square plus 0.5 square under root, right? और उसके बाद we have to subtract the original length and then divide by the original length. Okay, so this is what comes out, the value of the strain. Okay, in this this is unitless, right? Strain would have no units, so this is fine. If you multiply it with E, which is the modulus of elasticity, which is 210 gigapascal, you're going to have strain coming out in Pascal, जो कि उसको into थोड़ा सा rewrite करके you can just confirm कि it's 3.5 megapascal almost. ठीक है? So this was a little weird. This was a rather weird way of doing things and not very easily applied everywhere, right? If you want something a bit more systematic, then the systematic way of doing this would be okay, uh, use this transformation equation, right? So this transformation equation also available in your um, in this formula sheet, right? This equation reads के in the local coordinate system अगर coordinates q prime है, so that is equal to a transformation matrix multiplied by ये global coordinate system में जो coordinates हैं for a truss. So the way it would apply here would be k u1 prime u2 prime is going to be equal to this lambda multiplied by u1 v1 u2 v2. ठीक है, इसका यही order क्यों है? In order to understand that, you should go back to the derivation of where this transformation matrix, when this transformation matrix was derived. उसमें जो order इस्तेमाल किया गया था, हमने वही order इस्तेमाल करना है. And that is really the only thing that I would want you guys to maybe remember, because I can provide the formulas, I'm sure, but you're gonna have to know what these Q1, 2, 3, 4 mean, या in stiffness matrices में कौन सी जगह पे क्या लगाना है, right? That you sort of have to know on your own, right? So in our case, okay, in our case, u1 u and v1 is equal to 0, and we figured out that v2 is also equal to 0, right? So the only displacement that's happening is k in the x direction, point 2, node 2 is moving a bit to the right. So only this thing exists. And since theta is equal to 45 degrees, all of these terms जो कि exist करती हैं is just 1 over under root 2, right? So इसमें u1 prime, which is the displacement of this beam along this its own length, and u2 prime, which is the displacement of this truss along its own length, can be found. So u1 prime is going to obviously be 0 because this point is fixed, जो कि यहाँ से भी clear होना चाहिए कि it's 1 over under root 2 into 0 plus this into 0 plus 0 0, right? So it's just 0. And u2 prime is going to be 0 into 0 plus 0 into 0 plus 1 over under root 2 into u2 plus 0, right? So that means that u2 prime is just going to be equal to u2 divided by under root 2. So epsilon, which was du by dx in this case, like generally du by dx के form इस्तेमाल हो सकते हैं, is the change u2 prime minus u1 prime divided by the length of the element. ठीक है? So this difference is just u2 divided by under root 2 because u1 prime is 0, and you have to divide it by L1. L1 you might remember was 0.5 into under root 2. So यहाँ पे 0.5 into under root 2 can be rewritten as, you know, 0.5, either you can move it to the numerator, and instead of 0.5 down here, you would have a 2 up here, right? So it's kind of obvious k this just is going to be equal to u2, right? Under root 2 into under root 2 is 2, and 2 over 2 is 1. So that's why ये जो epsilon की value थी, this was coming out to be exactly the same as the value for u2. But keep in mind that this is absolutely a coincidence. ऐसा नहीं है कि epsilon और u2 are the same thing. They are absolutely not the same thing. ठीक है? So by the way, दफा u आ गया तो उसके बाद of course epsilon आ गया तो उसके बाद of course you would just have to once again multiply it by the Young's modulus to find the stress. ठीक है? So that was part one. Part two was the modal analysis, in which you had to also use the mass matrices. ठीक है? So mass matrix की general equation, यही equation mass matrix की applies for the first element and for the second element, right? And then you have to assemble them. So once again, इस तरह की complete assembly is absolutely not necessary. All we really have to do later on is focus on focus on this part, right, in the mass matrix, and focus on this part for the stiffness matrix, and agar zarurat ho to focus on this part for the force matrix. For the purpose of model analysis, the force matrix is not really required. We are going to just plug zero instead of that. Model analysis के लिए या national frequency निकालने के लिए force is really not important. ठीक है? But if you apply the boundary conditions, you are going to get rid of all of these little terms. अच्छा, by the way, ये सिर्फ थोड़ी सी context के लिए ये बात given है कि if my overall mass matrix is assembly of these two matrices, कि जहाँ पे this is यहाँ पे M1 आ जाता है और यहाँ पे M2 आ जाता है और जहाँ पे ओवरलैप हो रहा है वहाँ पे वैल्यूज आपस में ऐड हो रही हैं, right? So this overall thing is my mass matrix, and if you just like what's actually happening, the actual equation, the dynamic equation is that mx double dot, where x is the vector containing all of my displacements, plus k into x, which once again contains all of these displacements, is going to be equal to f. So घुमा फिरा के this really large weird looking equation is indeed mx double dot plus kx is equal to f, right? Okay, so what we are trying to do is, after applying the boundary conditions, you're left with just this part right here, which is 4004 multiplied by rho L over 6 plus ये 2002, जिसमें 2 को बाहर निकाल के just gonna get A over L 1001 is equal to the force. ठीक है? In order to find the natural frequency, we have to set the determinant of this K matrix minus omega square M matrix as equal to 0, right? So you have to find the value of omega that sets this determinant equal to 0. So K matrix was this thing right here, minus omega square into M matrix. इसमें ये 4 को मैं बाहर लेके आ गया, should be equal to 0. So that means that the determinant of iska pehla element basically is A over L1 minus 4 by 6 is 2 by 3. So minus 2 by 3 omega square rho A L1. So this element is 0 because ye bhi 0 or ye bhi 0 hai. This third element is 0 and the fourth element is once again the same element. Okay? So for this determinant should to be equal to 0, this value multiplied by this value minus this into this, which is 0, should be equal to 0. So for that to happen, ye ek value must be equal to 0, right? So this value must be equal to 0, which you can rearrange and solve for omega square. So omega square is going to be this much, and if you if you want to find omega is just going to be under root of this whole term. By the way, some interesting things come out of this. The area actually disappears. Agar maine ye sahi solve kiya hai, which I am sort of confident, but do have a look at it yourself as well. The area sort of disappears, which means that if I change the density of this structure, फर्क पड़ेगा, उस पे natural frequency pe. If I change the lengths, obviously फर्क पड़ेगा, but if I change the area, you're not really going to see any real change in the natural frequency, कम से कम in this mode. ठीक है? Okay, so plug in the values. It comes out to be तकरीबन 8800 radian per second. Have a look also at this example. Usme the answer is very different. I'm pretty sure usme the value of E that they use and the value of density as well is kind of different than what I'm using, but do have a look at it. I have a strange feeling that there is a calculation error in the book, not in, or there could be one here as well, by the way. There are different problems, but still अगर आप लोगों ने खुद सॉल्व करना है तो एक दफ़ा खुद भी चेक कर ले कि किसी में कोई कैलकुलेशन का एरर ना हो, बट द प्रोसीजर ऑब्वियसली इज pretty much the same. ठीक है? Thank you.